Okay, anybody have any homework questions you'd like me to go over? I want to talk about two things that are going to be important. The first one is the idea of a force where you know the direction but you don't know the magnitude. Okay. So force with a known direction but an unknown magnitude. Now, you could think of this as a force that has two unknown components, so in that you could easily represent it with two variables. But usually, almost always in statics, the game is kind of reducing the number of variables enough that you have enough equations to solve this big system of equations. So you're definitely not looking for ways to add as many variables as possible. You're trying to be stingy with your variables. So if you know that a vector is at an angle of, let's call this 40 degrees from the horizontal like this, and I'm going to use a standard coordinate system. And we're going to call the magnitude of this RT or something. Okay. So how would you represent that? Well, if you know that angle, you can represent this using cosine and sine by just, I said before that if that you take the counterclockwise angle from the positive x-axis to the vector, use cosine and sine, and then multiply it by the length of the vector. In this case, the length of the vector, we don't know what it is, but we know that we're going to call it the variable r. So this is just going to be r times the cosine of the counterclockwise angle here. You can think of this as 180 minus 40. And r times the sine of 140. And if you do that calculation, you get negative 0.766 r, positive 0.643 r. Okay, so you don't want to, if you know the direction, you don't want to represent these vectors as two unknown components. You're adding one unnecessary variable. You can see here this thing is all in terms of one variable. Okay. Yes?
Would you rather us give the right or the left for our answers?
The what?
Would you rather us leave it as like code?
Oh, I see. Yeah, actually, I would prefer that you put it into like decimals. And I don't really care how much you round. I usually, for things for decimals under 1, under a magnitude of 1, I think I usually use 3 decimal places, and for everything else I use 2, but that's just kind of random. That's what I've gotten used to doing. I don't know. I'm used to doing it this way, maybe because, I've always done all these calculations with big computer programs, and in big computer programs, that's what you have, is you're just dealing with decimals and stuff. Okay, so this is in the case, this is the way to do it for a 2D problem. When you're given angles. What about a case where you're not given angles, you're just given reference points? So if instead of angles, you're given reference points. So I'm going to still do this in 2 dimensions just because it's so much easier to draw. But let's say that we have a case where this object is connected to, I don't know, say this is the object that we're looking at, and there's other stuff going on with it. We don't know what that is. But this is connected to the wall by a cable. And we're not, instead of given the angle that this cable is at, let's say that we're able to figure out coordinates of these 2 points. So let's say this is 16.5, negative 8.0 in meters. And then this one would be, let's say 14.5, negative 7.0. Okay, and we don't know what the tension of this cable is usually at the start of a problem, but let's say that the cable, we're going to call this cable tension T. What's the force vector applied to the block by the cable? And by the way, well, I'll say that at the end. Okay, so, well, what's the direction of the force this cable applies to the box? You'd have to remember this from Physics 1, but this cable force goes away from the body toward the other side of the cable. So we know that the direction is that way, okay? And so this force vector then is going to be, I'm going to do it in a couple of steps. I'm going to first figure out a vector that goes to the wall from the block. Then I'm going to calculate the unit vector in that direction, okay? Which, notice that in this angle version, a lot of times we don't think of this as a unit vector, but this cosine and sine, since cosine squared plus sine squared is equal to 1, you can tell that this is a unit vector, okay? So that's what we're doing here. We're just using cosine and sine to come up with our unit vector in the right direction. And in this case, to get the unit vector in the right direction, we're going to figure out the vector that goes from the block to the wall, normalize it to get the unit vector in that direction, and then multiply it by t. Okay, so we're going to go, I'll write it as, first, the vector, before we make it a unit vector, is going to be the destination point minus the origin point and so that is negative 2, positive 1. But that's not a unit vector. So now to get the unit vector, we're just going to divide both of these components by I'll write it as, so we're going to go 1 over square root of 2 squared plus 1 squared And so that is 1 divided by square root of 5. So this is negative 0.894, positive 0.447. And so then the force vector that's applied to the block by this cable is equal to this times our variable magnitude. So you get negative 0.894 T, 0.447 T.
You just put the T out front.
Yep. I mean, once you get into the equations, eventually you're going to have to, multiply it out anyways to separate the components in the equation. Okay, so this is the approach. Okay, so this first one is if you have a 2D problem and what you're given is angles. This other approach is what you're going to use in pretty much any 3D problem. Or 2D problems where you're given points instead of angles. Okay, so any questions?
Sorry. How did you said something of knowing when it's a unit vector and when it's not?
Oh, well, yeah, you can always, if you calculate the magnitude of the vector, a unit vector has a magnitude of 1. So if you ever want to check, I mean, if you calculate the magnitude of this vector, you get square root of 5. And so it's not a unit vector. If you did the same thing now and calculated the magnitude of this u hat, that the hat caret thing means a unit vector. So if you calculated the magnitude of that, you'd get 1.
Is that a pretty consistent convention?
Yes. Yeah, pretty much universal. Any other questions? Okay, another thing that comes in handy a lot of times is in 2D problems where you are dealing with angles. A lot of times you're going to have an angle from some reference, and then the angle you want is going to be in reference to the second thing or whatever. It can get a little confusing if you're just trying to do it in your head. I don't know. I'm going to call it piggy. I've never called it this before. We'll see how well it takes. But I'm going to call it piggybacked angle references. I don't know. Sounds stupid. But here's the idea is, so let's say that we have a wall and there's a slot here. Let me make that a little shallower. Okay, so you got this slot, and there's an angle between the wall and the slot of 70 degrees. And we want to represent a vector with the magnitude r that's perpendicular to the slot. This is a lot like one of the homework problems that you're going to get for before the next class. Okay, so this kind of thing, figuring out the angle, usually you're used to just doing it in your head or it just even popping into your head or whatever. So you get a little alarmed sort of naturally when you see problems where doing it in your head kind of short circuits your brain. Just be very systematic. Just write out the coordinate system. And then just go vector to vector. And if you, just going one reference at a time. Okay, so there's the coordinate system. And let's start putting down the vectors that matter in this case. So, and any line you can represent with either one of two vectors. Okay, you can, like a vertical line like the wall here, you can represent it with an upward vector or a downward vector for this. So I'm going to represent the wall with a downward vector. Okay, so here is, that's like the first reference vector that we're going to use. And the reason I'm going to do that now is to get to the slot, you can see the way I have that angle drawn, I'm going from a vector pointing this direction to a vector pointing this direction, and I know those are 70 degrees apart. Okay. And then I want a vector that's perpendicular to this one. Well, you have two choices of perpendicular vectors. I guess I'll do this one. Perpendicular means that that angle's 90 degrees. Okay.
I'm sorry, is this in 2D?
Yeah, it's in 2D, yes. In 3D, you're basically not going to be using angles ever. You're just going to be using points pretty much. Okay, so now we're trying to figure out the counterclockwise angle from the positive x-axis to this vector here. Okay, can you see my cursor? So to do that now, we can just go, come back. So theta, so this is the one we want. So how do we get that angle? Well, we can go, we're just going to hop from vector to vector. I'm going to first go clockwise 90 degrees from the positive x-axis to get to that downward vector. So negative 90. Okay. Then I'm going to go clockwise another 70 degrees to get to this one. And then I'm going to go clockwise 90 degrees to get to this one. And you get an angle of negative 250. I also could have, the numbers could look different, but when you use cosine and sine, it would have been the same if I would have called it a counterclockwise angle of 270 to get to this one, and then minus 70, minus 90. Okay. And so now this unit vector representing the vector we want here is cosine of negative 250, sine of negative 250, let me plug that in. Okay, so you got negative 0.342, 0.940. And so the force vector then is just this unit vector times the variable r. So negative 0.342 r, positive 0.940 r. Any questions about that? So So yeah, in 2D, sometimes you'll use angles. A lot of times you'll use angles. And this is some ways to work with angles to get the unit vectors that you want. In 3D, to get unit vectors, you're pretty much always going to just subtract coordinates and then normalize it to give you a unit vector in the direction you want.
So really what you're trying to get across is just to be systematic.
Yeah, and so be systematic is always good advice, and this is the system. Be this systematic. Okay, so now let's go on to particle statics. Okay, so a particle is really just like a treatment of an object. It doesn't mean necessarily that the object is small or anything like that. It really just means that you don't care about the object's orientation through time. So it means that you're treating an object as having no length dimensions. And you're treating this object as existing only as a like point size object at its center of mass. So let's say exists only as a point at the center of mass. It's pretty natural for people to think of particles as small things because like particle physics is subatomic particles. And there are reasons why for very small things, there's no reason to treat them any way other than particles. But you know, if people are doing like planetary motion calculations, they're treating planets like particles. And to us, we don't think of those as small, you know. And because we're treating this as having no length dimensions, we can't tell differences between the left side of a particle and the right side. So therefore, we're ignoring changes in object orientation. And I'll mention this again, but there's always kind of a natural connection between circular motion and changes in orientation. But so what I'm saying about a particle can move in circular motion, no problem. We can track it in circular motion. It's doing this, you know. What we can't track is it doing this. And they're related because when an object is doing this, an object that has length dimensions, every point on that body is in a circular path around the center. That's why it can get confusing between these two things. But when I say changes in orientation, I'm saying first it's looking this way, second it's looking this way. We don't know anything about that with particle calculations. Okay, the only governing equation for particle statics is Newton's second law. And it's Newton's second law for zero acceleration. And it just says that the net force on the body is equal to 0. This gives you 2 equations if you're doing a 2D problem, and 3 equations in a 3D problem. Okay, anytime in this class you use Newton's second law, and we're not going to be talking about the moment equation yet, but we're going to use that a lot too, so I'm going to put that in here too. Anytime you use Newton's second law or the moment equation, you need to draw a corresponding free body diagram. And I'll just abbreviate those FBD. So let me give you the steps for drawing a free body diagram. In Physics 1, I think probably a lot of you got in the habit of drawing your free body diagrams. Drawing your free body is like a point, like a particle, and then you have the force vectors going out from it in different directions. Since we are going to be doing mostly in this class rigid bodies, things that have length dimensions, we're instead going to draw like an outline of the actual body. You don't have to be too artistic about it, but it has to be accurate enough to show the different sides, the top and the bottom, give you sort of a sense of what's included in the free body and what's outside the boundary. So step 1 is draw a closed outline of the chosen body. The whole idea of a free body diagram is you make it very clear to yourself and whoever else is looking at it, the distinction between the stuff that's in the in crowd and the stuff that's outside of the boundary. So the only thing that matters is this boundary. There's not going to be any details on the inside. There's not going to be any, no matter how pretty the environment is, there's no drawings of trees or anything outside the boundary. It's all you care about is that boundary. So no internal details. And no external objects. That's the free and free body diagram. Your picture is free of anything except your chosen body, okay? And everything else is just represented by forces. Yep.
Even the ground?
Even the ground, yeah. If that's outside of your chosen body, then don't draw the ground. Yep. And second, draw all load vectors. And by loads, I'm talking about forces, of course. I'm also talking about couples later on, so I'll go into the definition of couples when we get there. For particles, there's no such thing as moments and couples and stuff, so we don't have to worry about that yet. But I'm going to break, okay, draw all the load vectors and be very specific. These are the load vectors acting on the chosen body. We don't care about loads that the chosen body is applying to the surroundings, and we definitely don't care about forces and stuff that the surroundings are applying to each other. So to represent these, if the direction of a load is known, draw this as an arrow in the known direction. And then just label it with a scalar variable or value, a number variable or value. So that would be something like, okay, if you know the direction is this way, and label it with like an R or whatever you're going to use for the variable. And then in the equations, the way you would represent this is this R times the unit vector in that direction. Okay, if the direction is unknown, that happens sometimes too. So if the direction of the load is unknown, draw those forces as like a small sort of coordinate system. And label it with a vector variable or value. Okay, so that would be like in 2D, you would do it like this and label it R as a vector. And that says we don't know any of those components. Okay. So you also see people do it like this. It means exactly the same thing. Where this one is the X component of the vector, this one is the Y component of the vector. You can do either one of those. The one on the left is the way I do it. And in 3D, same thing. Like that. How do you know when your free body diagram is complete? So first, it has to have the weight of the object in it. And here I'll say, and any other field forces. In this class, I don't think any of my problems have field forces other than weight. But that would be like a magnetic material in a magnetic field, or a charged material in an electric field or something.
Because weight is dependent on gravity, does that mean gravity is considered a field force?
Yes.
Okay.
Yep. And then just go around the whole boundary looking for contact with the surroundings. Once you have once you have a load for each contact point, you're done. Okay, so I think this can be a helpful thing to remind yourself when you get into complicated problems with a lot of stuff going on. So here's my example of a complicated problem with a lot of stuff going on. So let's say you got this mud, and stuck in the mud is this truck. It's a Mercedes Sprinter van.
That's exactly what I was thinking.
And then standing on the roof of the truck, probably having caused this whole fiasco, is this giant bird. Pretty tail, though. And then standing over here, assessing the situation, is the driver. And then helping the driver get his truck out is this helicopter.
It's like a Michael Bay movie.
Yeah, that's true.
I was thinking this is like in the Australian emu wars.
That bird is inspired by the bird from Up. Okay. He has very weird posture.
It's just a car wreck, so yeah.
Yeah. Okay, so okay, so and then this bird is also being yanked on from its leg, and I guess maybe by a big fish. Mudfish.
You should put like a cowboy hat on so he's laughing.
Yeah. That would be unrealistic. Okay, so anyways, draw a free body diagram of the truck is the point here. Okay, so I'm going to draw an outline of the truck. I know that the weight is acting on the truck, so I don't know what the mass is, but whatever it is, call it capital M. Multiply it by 9.81 meters per second squared, and that's the weight. Okay. And so now that we've dealt with the weight, that's the first one of these two. Now our only job is to go around the boundary of the truck and account for every one of these contacts. Okay, so I'm going to start at the front wheel and work my way around counterclockwise. So the first thing that's in contact with the truck is the cable. Cable forces act away from the body, parallel to the cable. So I'll write that as T. Okay, and then the second force is a contact force from from the man. I'm going to treat that as just a force pushing down. And then there's a contact force from the emu. And then keep going around to where the truck is in contact with the mud. And I don't know the direction of that mud force, so I'll just call it F mud. Hold on. F mud. Okay. And so there's no reference to the helicopter. There's no reference to this fish, because your only job, I mean, clearly those things influence what's going on in the problem, but your only job in a free body diagram is to find the points of contact with the surroundings and represent those. Okay, well, this is something, I mean, we have all these variables. We don't have enough equations to solve this the way we have it, but this is a complete free body diagram. And then in order to solve it, you'd have to go and say like, okay, now I'm going to isolate the emu to figure out this force, or now I'm going to isolate the, the bird or whatever. That is the emu, but you know what I mean? Go around and isolate other things. But for this body itself, this is all we can say about it. Yes?
Does the fish not change the angle that the emu is putting force on the truck?
Yes, you are right about that. You are right about that. I don't know what this, I think we just wouldn't know what this force direction is. Thank you. That's something we'd have to figure out later. And I'm going to talk about like how you know the directions of forces and stuff. I'll talk about all that. But for now, I just want you to notice like this super complicated thing. It's sort of the same way that I said your brain just sort of, your eyes just kind of glaze over what sometimes when you see something with all these different angle references. But just remember to be systematic about it. There's a system. Just stick with the plan. You know what I mean? And same thing here. There's all this stuff going on. Your brain, there's a tendency to sort of just see it and freak out and not know what to do. But just remember, all you're doing is wait and then find those contact points. And then follow the rules that we'll be spending a lot of time on to determine, do we know the directions of those forces? Don't we? You know, that kind of stuff. Okay, so contact forces. There aren't too many types of contact forces that we're going to see with particle statics. The three that we're going to see are cable forces, frictionless contacts, and friction contact. So I'll start with cable forces. A cable applies a force to a body. That's parallel to the cable. And away from the chosen body. So for example, if you have a setup like this with a cable going over a pulley, and on one side it's connected to, let's call the one on the left box 1 and the one on the right box 2. Free body diagram of box 1 would have the weight force down, and I'll call that M1 times G. And now going around the boundary looking for contact, the cable force is the only other contact, and that's going to be parallel to the cable, away from the body, and so that. And then the free body diagram of box 2. You have the weight of the mass of box 2 times 9.81. And then the only place the surroundings make contact with box 2 is the cable. The rule says the cable force is parallel to the cable, away from the body. So those are 2 complete free body diagrams. What's required for these 2 T's to be the same? So we're usually going to assume they're the same. Yeah.
They're not moving, or no acceleration.
Actually, even if there was acceleration, those 2 would be the same under some conditions. So those conditions are a massless and frictionless pulley. And I guess actually a massless cable in this case, because we're isolating the boxes. So let me get that in your notes. So notice these cable tensions are always the same for massless and frictionless pulley. And massless cable. Why don't I just start with that, and I'll do the 2 types of contact forces, frictionless and friction contact, next time. Remember that there's no school on Monday, Labor Day. So I'll give you an assignment, but it's going to be due on Wednesday, not on Monday. Okay, that's all.